All right, good evening, everybody. My name is Amalia Weber. I am the program specialist at Rochester Hills Public Library, and I'd like to welcome you to this evening's program, Smart Towns program, If Mud Could Talk, How Coastal Sediments Can Reveal Thousands of Years of Natural Hazards. Before we get started, I'd like to take care of a few housekeeping details. Firstly, tonight's program will be recorded and available to view about 1 week from tonight on our YouTube page and on the RHPL website shortly after. We ask audience members to please silence or turn off their cell phones before we begin in order to avoid any disturbances during the presentation. The Friends of the RHPL 7th Annual Wine, Wit, and Wisdom Fundraiser is taking place here at the library on Saturday, April 30th from 6:30 to 10 p.m. Participants can attend 2 speaker presentations from a choice of 6 and enjoy a buffet dinner, drinks, a silent auction, and a 50-50 raffle. Registration forms are available at the circulation desk, or you can visit rhpl.org/friends for more information. Our next program is Women's Experiences During the Holocaust, which will take place on Thursday, March 10th at 7 p.m. You can sign up for that at calendar.rhpl.org. Tonight's program is presented in partnership with Smart Towns, a lifelong learning program for everyone in the community, led by educational organizations in Rochester, Rochester Hills, and Oakland Township. Smart Towns offers lectures, presentations, and courses that introduce participants to all aspects of the topic and are presented by experts in their respective fields of study. And without further ado, please welcome our presenter, Thomas Bianchette.
Thank you. You know, the first thing I was going to say, I was going to joke that I took this picture today on campus. But we know that that's not true because it's nice and bright and warm looking. And I don't want people to get mad at me. The ones that were really, really focused and really yearning for spring, they get kind of mad at me for that joke. But it's a very nice picture of Oakland University, where I am assistant professor in the chemistry department, and I'm faculty in environmental science. So this talk right here is of interest for anyone that has interest in geology, oceanography, climatology, risk assessment, policy, economics even. Okay, so this is where all of these backgrounds and all of these multidisciplinary topics, they essentially merge into one. So going to be talking about sediments. I'm a sedimentologist, PhD from Louisiana State University in Oceanography 2014. So I will be talking about sediments, how sediments can reveal natural hazard histories. So if mud could talk, what would the mud tell us? So essentially, as I stated, multidisciplinary natural hazards, climatology, sedimentology, and so on and so forth. So I'm looking forward to having fun. You look like a fun group. So let's get started with this. Yeah. I have a blaster, but the microphone's still. I will talk softer. I'll have to contain my excitement, but I will talk softer. I will talk softer. The first impression of hurricanes, when you think of hurricanes, and people from all over the world think about hurricanes in different ways. I grew up in the area. I went to Harlan High School. I graduated from Harlan High School. So growing up in Southeast Michigan, you have different views and feelings of hurricanes, especially if you never lived through one. So writers and artists, they may think of their beauty. Very, very beautiful eye and eye wall and counterclockwise winds and all that stuff that you see on the Weather Channel if you're interested in severe weather and storm chasing and storm tracking and all that stuff. There's poems about storms and tempests and all that stuff. There's also beautiful artwork. showing waves and surge and all those types of paintings. They were very, very famous paintings, like the one on the right-hand side from 1944. Now, most, especially those in very vulnerable coastal areas, low-lying coastal areas, they don't see it this way. They have experienced very, very devastating losses. Losses to property, losses to life, losses in economic opportunities. So there have been countless hurricanes that have impacted the United States Gulf and Atlantic coasts over the last few decades. And I'm going to be talking about this a little bit later. So too many to count pictures from Dorian and Michael and Irma. Pictures everywhere, okay? Devastating winds, sustained winds, very, very high and fast, rapid wind gusts, towering storm surges, and so on and so forth that cause a lot of devastation. And this is a very, very common issue in the U.S. coasts. It's a very costly issue, and it demands much of our attention. In all my classes that I teach, I always say that natural hazards is one of the most diverse topics in terms of all types of stressors that occur from these natural hazards, whether there are environmental stressors, okay? So these are all examples of peer-reviewed studies, okay? These are just the topic page, the first page. So mangrove forests, economic damage from hurricanes. Right here, social damage from hurricanes. So PTSD, you get flooded from Hurricane Katrina, for instance. You lose everything you have. You essentially pick up and move to essentially start a new life. You move to Houston, you move to Baton Rouge, and you get flooded again for a second time in a decade. So you essentially, and there have been cases of this, of having PTSD from losing everything that you have, not once, but twice in a matter of 10, 12 years. So no matter if you are a social scientist, a physical scientist, natural scientist, environmental scientist, there is an aspect of natural hazards that pertains to your field of study. If you study infrastructure, if you study water quality, if you study all these different topics, there's something that pertains to your expertise. So I moved down to Baton Rouge, Louisiana in 2005. Parents dropped me off, said, see you whenever, see you never, right? They dropped me off and they said, peace, I'm out. 2005, 2 or 3 weeks after I landed in Baton Rouge, was Hurricane Katrina. So I often say that a lot of times you pick careers, but sometimes in life, the careers pick you, okay? And I had I did not know I was going to be doing hurricanes when I landed in Baton Rouge. I just wanted to do something science related. So this essentially picked me. This field picked me when I saw all of the devastation that occurred in and throughout the South Louisiana area for weeks and months in the future. Okay, so we're talking loss of life, we're talking economic damage, hundreds and hundreds of fatalities. There was intense flooding, the levees breached, okay, there was looting, there was murder, there was all types of very, very bad things that happened in the aftermath from Hurricane Katrina. Lots and lots of economic damage occurred from this storm right here in 2005. I think it was this storm. The U.S. had a lot of very, very bad and intense storms that made geologic impact and made social impact. But I think that it was this storm that really got the attention of a lot of people in the United States about the severity of these types of events. And you see pictures of the Superdome, you see flooding, and you see all of the work and evacuations from FEMA, the U.S. Navy, and so on and so forth. Now, I wanted to talk about this. I want to show this graph right here because I'm going to be talking about categories a lot about hurricanes. So this is just an introduction to categories of hurricanes if you have not heard of the Saffir-Simpson scale. Saffir was an engineer. So I'll be talking about categories 1s, 2s, 3s, 4s, 5s. 3, 4, 5 are considered major hurricanes. So we're talking about sustained winds of 111 miles per hour and up. So that's very, very fierce. We all got really bad winds 3, 4 days ago. I think it was 3, 4 days ago. We got really, really bad gusts. I think on that day, the sustained winds were in the 30s. I think the gusts were in like the 50s. So we're talking about sustained winds that are over 111 miles per hour. And the gusts are much, much more fierce than that. So this is just a reference to the scale. I'm going to be talking about categories a lot, especially categories 3, 4, and 5, which are major hurricanes. Now, what do we know about hurricanes that hit the United States? Okay. Now, this is a really fun website. It's the website that is operated by NOAA. So I just took these little 15, 16-year chunks to kind of piece together the recent hurricane history that we have experienced in the Gulf and the Atlantic coast of the United States. So these are all North Atlantic Basin hurricanes from 1973 to 1988. There are 28 events. Now, not all of these made landfall on the United States. Some of them may have curved and made landfall essentially nowhere because they go into the North Atlantic Ocean and then they essentially lose steam and dissipate and don't make any damages at all. So we had 28 events in this time period. We move on to the next 15-year span. So we go from 28 events to 45 events. So the spaghetti diagram gets a little more busy, okay? 28 to 45 events. So you see all these squiggles, you see a lot of activities right here. So now we go to 2005 to 2020. Now we have 55 events. So I often ask my students, I say, what can you gain from this? And if they're stuck, I say, you can just give me a broad answer. You don't have to be very detailed. And if they're still stuck, I can just say, there's a lot going on, right? There's a lot going on here. So we have 55 events in the last 15, 16 years. This does not count 2021. So this has our attention now. But everything that's going on in the Gulf Coast and the Atlantic Coast in terms of hurricane damages. The economic toll, the loss of life, loss of infrastructure, and so on and so forth. Now, I want to take a truncated snapshot of 2 of these seasons. Okay, so this is 2017 and 2018. Okay, I don't know if anyone in here is a big weather buff and follows weather, watches the Weather Channel, and so on and so forth. But so this is not every hurricane in the 2017-2018 season, but these are some of the very severe major hurricanes. And this is just 2 hurricane seasons, okay? This is just 2 hurricane seasons, and these were very, very severe hurricanes that made landfall on the United States or our territories. First, maybe you remember this or not. Hurricane Maria. Does anyone here remember Hurricane Maria? Anything about Hurricane Maria? Hurricane Maria kind of made a loop and kind of went due east. But what did Hurricane Maria hit? Right here. What is that right there? Does anyone know? Puerto Rico. Very good. Puerto Rico. So these are all of the major statistics and the very eye-opening damages. Over 70 billion in damage. A lot of beach erosion. When there's a lot of beach erosion, then you are really impacting the local economy, because Puerto Rico is very dependent on tourism, very dependent on nice, lush beaches. Mudslides. Puerto Rico is very hilly. It's mountainous, okay? So we have very, very intense, prolonged rainfall, and it created mudslides. 100,000 people without power for 7 months. I cannot even fathom. I lose power for 7 hours and I'm losing my mind, right? So 7 months, 100,000 with no power, may have been responsible for 4,600 deaths. Death tolls there are always estimates to the death tolls, okay? So this was in the 2017 and 2018 hurricane season. This is Maria. I'm not even close to being done yet. We have Irma. Maybe you remember Irma. Essentially went right up the spine of western Florida, 70 billion in damage, sustained winds, 180 miles per hour, over 50 fatalities. If you follow this like I do, it's almost like it happens so often. Students are in my office are talking about hurricanes. I can't even keep them straight in my mind anymore. That's how frequent they happen. These are very, very major, powerful events. Michael, sustained winds 160, over 25 billion damage, over 30 fatalities. So we go to Harvey. So Hurricane Harvey is one hurricane that really, really caught our attention, okay? Policymakers, the US government, and so on and so forth. It really got us concerned. If you remember anything about Hurricane Harvey, it got us concerned, and you see this kind of weird track type where it kind of went like this, then it kind of came back, and it kind of went up the Gulf Coast. So why did it make us very, very concerned? 130 mile per hour winds, 125 billion, it's billion with a B in damages, over 100 fatalities. But in addition to this, it was the physics of this hurricane that really concerned us. There's 3 main reasons why this really concerned us. Number 1, it essentially intensified from a Category 1 to a Category 4 hurricane very, very quickly. So intensified very, very quickly. Not common, okay? To intensify from a 1 to a 4 in, I'll say that's maybe 50 miles or so. Not common. It hit a warm water eddy and went from a little minor Category 1 or tropical storm to a Category 4 very quickly. So that's 1. Number 2, it essentially stalled between a northwest and southeast landmass that got caught. And it stalled. And it rained. And it rained. And then it rained. It rained and rained and rained. So it stalled. So that's 2. Number 3 is that it caused a lot of inland interior flooding, okay? And how it did that, because it stalled so long, it essentially picked up the water that it deposited on the land. So the land was essentially its fuel source, okay? Very, very uncommon. So you have those 3 characteristics. Those 3 characteristics combined really concerned people. It made more or less, not direct impact on Houston, but it hit very, very close to Houston. Caused lots of flooding. A vast majority of Houston residents did not have flood insurance. So they lost thousands and thousands of dollars of property. This is a colleague, an old colleague and friend at LSU, Dr. Nina Lamb from Louisiana State University. So when this came out, this was in the Washington Post. This was a story that she published in the Washington Post that essentially stated, and this was in response to a lot of these hurricanes, especially Hurricane Harvey, that you can move to get away from these hazards. Just because you move inland, that doesn't necessarily mean that you are safer. Coastal construction in flood zones in the United States is actually not increasing. It's not increasing, believe it or not, on the coast. Inland interior construction in flood zones in the United States is increasing actually in a lot of areas in the South. So there is often this misconception of, I flooded, I lived in New Orleans, I'm gonna move to Houston. Those residents got flooded twice. Houston is a little bit further interior than New Orleans. Or you get flooded from New Orleans, you move up to Baton Rouge, Louisiana. Baton Rouge, Louisiana in 2016 had a 500-year flood event. So just because you move interior, you're not really safe from flooding per se. So what do we know? What do we know about hurricanes? Okay? Does anyone know the age of the Earth, roughly? I'm sorry?
5 billion?
Close. 5 billion, you said? Yeah. 4 point. Scientists fight about this because they fight about everything. 4.5, 4.55, 4.6 billion. Okay? 4.6 billion years. And we know that a lot has gone on in 4.6 billion years. Okay? Moving continents, Pangea, and shifting continents, shifting continental shelves. Now, when we talk about hurricanes and what we know about the historical record of hurricanes, now, starting in the 1960s, okay, is when we started to have the implementation of geostationary satellites. So in the 1960s and beyond, we were good. We had really good records, track records of hurricanes. 1960s and beyond, okay? When we get into the 1940s to 1960s, we're doing a lot of aircraft recon and things like that to really determine hurricane tracks and so on. Beyond that, we're relying on ship logs and diaries, literally, to really get hurricane records. So it is really amazing to say that beyond, and this is us right here, the Caribbean Sea and North Atlantic Basin, these are just examples of some newspaper documents, because scientists, when you get into the late 1800s, they cobble together diaries and logbooks to really determine old hurricane records, and that's how they piece them together. So it's really amazing that 1851 is our baseline for knowing what's going on with hurricanes. 1851 for the Caribbean and North Atlantic. So 1842 in the Indian Ocean, Western North Pacific, so we're talking China, Japan, and in that area, 1884. So really mind-boggling here, the Eastern North Pacific. So Eastern North Pacific, we're talking about Western Mexico. So if you vacationed in Cabo San Lucas, Acapulco, Puerto Vallarta, those areas are very, very reliant for tourism dollars. There's nice beaches, restaurants, downtowns, and so on and so forth. 1949, okay? So when they are calculating and determining hurricane risk, they're looking at 70 years of record. So it's not unreasonable to say that they are lacking in a lot of information that can help their overall risk assessment in these areas. 1949. Now, if you follow hurricanes, if you watch the Weather Channel, what impacts hurricane frequency? This is the most common answer, okay? The weatherman will just say, especially if you live in the Gulf or Atlantic coast, it's going to be active or inactive because it's La Nina, El Nino. Then that's it. That's all they say, okay? El Nino, I really don't want to get too much into the oceanography of El Nino. El Nino is nothing more than the strength and direction of winds in the Pacific Ocean, which impacts the temperature of the Pacific Ocean. It is a major climate driver through our entire globe. ENSO, which is the acronym for El Nino, Southern Oscillation, is a 3 to 7 year cycle. So this is essentially an annual time scale. So El Nino events from 1851 to 2020 in the North Atlantic, a lot of spaghetti, a lot of lines, kind of hard to really determine. 99 events, so 99 hurricanes during El Nino, 143 during La Nina. So that's essentially where scientists kind of leave it, okay? La Nina, you're going to expect a little bit more. You see 143 events versus 99. So that's interesting and good information, but we want to know what goes on beyond 3 to 7 year cycles, this kind of annual as El Nino, La Nina. Atlantic multi-decadal oscillation. So now we're kind of going beyond the annual and we're going towards decadal. This is just a lot of spaghetti models. The Atlantic multi-decadal oscillation, acronym is AMO. The AMO is a major climate driver for hurricanes, for moisture, for fish populations, and all sorts of things. So scientists Goldenberg et al. Concluded that during a warm AMO, it's very active in the Caribbean Sea and going into the Atlantic during these years. So we have these kind of 17, 18-year time periods. For here's 5, 6-year time period. And then a cold AMO is inactive. We're doing better, right? This is something, right? So we're kind of expanding and talking about multi-decadal, but we're not done, right? This is not all the information that we want to determine about hurricane risks in these areas. So scientists make this face, okay? Because they are trying to determine how to improve these records. I'm sure I've made these faces a lot, okay? Whether it's this face or this face, how do we improve these records to get beyond this active, inactive, going in just years to decades? How do we do this? It's something that we think a lot about. Now, we're going to turn things a bit and talk about the coastal impacts of hurricanes, okay? Now, hurricanes do a lot to coasts. One of the major drivers or one of the major geological impacts of hurricanes is all types of names of this, okay? Sediment fans, sand lobes, overwash, sedimentation, big sand things, you call them whatever you want, okay? But essentially, when there are low beaches like this, there is storm surge. Storm surge is wind generated. So the storm surge, let me orient myself. The storm surge essentially passes over these coastal sandy barriers and essentially transports the sediment onto coastal areas. So wetlands and lakes and swamps and all this stuff, okay? So it deposits these very, very nice sand lobes. So these processes get scientists kind of thinking, okay? Gets them thinking about the impacts of hurricanes and how this can possibly be interpreted in long-term, multi-centennial to millennial timescales. And this is just a very, very nice image of sand lobes. This is published on the website of the USGS, which is the United States Geological Survey. And nowadays, if you're looking at geological impacts of hurricanes, you don't need to wait for the USGS anymore. You can fly a drone. You can fly a drone in any risk or any damaged area from a hurricane, and you could take very, very nice images just like this. Now, so the premise of this talk, we have these hurricanes. We know that they cause intense geological or geomorphological damage. How can we put this together? How can it speak to us to give us good risk assessment or good climatological histories of these areas beyond El Nino and AMO and all those drivers. They are just years to decades in the past, okay? Now, this right here is Dr. Cambu Liu from Louisiana State University. He is my colleague and collaborator. He was my advisor for, I can't even tell you how long. It was a long time. 13 years. I think even longer than that. So he is an expert, a world-renowned expert in sedimentology and paleoenvironmental reconstruction. Now, few of you may know or may not know that by extracting sediments, sediments are essentially a history and archive of our Earth's history, okay? They are archives. So he pondered in the late 1980s, he and his student were out in the field, they were in Alabama, and they were kind of wondering this. Can geological records contain evidences of hurricanes? And similarly to what I just said, we have these Atlantic, Gulf of Mexico, activity periods, inactivity periods, and so AMO and all that stuff. Are these also on centennial to millennial timescales, going back hundreds of thousands of years? Is this possible? So he pondered these questions, and now he is known, he's very famous in this field, he is known as the father of Paleo Tempestology. You're like, what? What is that? Paleo, past. Ology, study of. Tempest, a storm. So it is the history of storms. Using, I'm not going to talk much about archival techniques. There are all types of techniques. There's biological techniques, there's chemical techniques. I'll talk about those a little bit. I'm going to focus largely on geology. I could talk about corals, I could talk about tree rings. I'm going to focus right here on coastal sediments, is to find evidences of hurricanes in coastal sediments. So this field has taken me to all different countries and areas along the U.S. Gulf and Atlantic coasts. This is a picture of Dr. Liu in Honduras, and we have these very, very nice sediment cores, and you see these white layers right here. These white layers are sand. These sand layers are indicative of old hurricanes. So the very, very basic premise is, you take long sediment cores, you count the sand layers, you perform radiocarbon dating, and you can determine how many sand layers have occurred in 500, 1,000, 2,000, 3,000, 5,000 years. It's not that simple. It's not that simple, but this is the premise of this field. This is Paleo Tempestology. So you can ask yourself all types of very relevant research questions. What is the probability for a given location to be hit by a catastrophic Category 4 or 5 intensity? These types of questions are very important. When Hurricane Katrina hit New Orleans, Hurricane Katrina was a strong Cat 3. Everyone talked about how that was the storm of a lifetime, how that storm has never happened ever again. But we really don't know that. We really have no idea, because the records only go back to 1851. In the year 1800, there could have been 5 Katrinas. The year 1750, there could have been a Katrina every day. Of course, that's not likely, right? But we don't know that. So we can determine this looking at geology, looking at geological records. How does landfall probability vary temporally? Is it more active on the Gulf? Is it more active on the Atlantic coast? Which areas of the United States are more active? Is there multi-centennial to millennial scale variability? Are there periods of geological time or periods of the past that are active or inactive going on these 100 to 1,000 year timescales. Are they related to large-scale climate mechanisms that are beyond what we know about ENSO and the AMO and those climate mechanisms that I talked about prior? So these are all relevant research questions that can be asked. Now, the premise of this is that you take sediment cores from a lake. So this is a very hypothetical lake setting, and these overwash fans, we talked about the overwash lobes, they thin with distance. So theoretically, core A would be full of sand because it would be so sensitive, it would get sand layers from very, very minor events. Whereas core C would only get the most extreme, the most intense events. So if you capture these sand layers, you can perform dating on the sediment and you can get a return period. Now, the best way to do this type of analysis is if you find what's called a modern analog deposit. So a modern analog deposit is from a recent storm. So this right here came from my master's thesis. Actually, this was the overwash deposit from Hurricane Ivan in 2004. We know that this was Ivan because our research group took cores from this lake going back many, many years. So this was not there before Ivan, and this was there after Ivan. So if you have a sand layer of this thickness, then you can use that to better calibrate your record. So, and you know, because this is Ivan, you know the wind speed, you know the storm surge, you know all the parameters. So if you see something in your record that is as thick or thicker, then you can suggest that this layer down below was a storm of similar intensity and or similar track type. So on the opposite end, if you see a thin layer, then you can hypothesize that that thin layer either came from a less intense hurricane or a hurricane that made landfall further away. So this is the modern analog approach. So as time has gone on, there have been a lot of studies looking at paleotempestology. This right here is from 2004, and this, I like this study here because it shows hurricane deposition on historic or recent sediments. So you have the imprint, you see the sand layers right here. This was on the Atlantic coast. I think that this was in Cape Cod, or the Cape Cod area. You have the hurricane imprints of Hurricane Carol. You have a hurricane in 1938. And you have a nice cross-section here. It might be kind of hard to see, but you have all these sand layers right here. Now, so this shows it on a historic. So this is kind of proof of concept, okay? We can date this by using cesium-137. You might be asking yourself, well, how do you know that this is Carol? How do you know that this is from 1938? If you know anything about cesium-137, cesium-137 is essentially a marker that's been distributed throughout most of the globe because cesium-137 is a byproduct of nuclear weapons testing, so from the 1960s. So this cesium-137 is essentially a marker, and it spikes during the peak of nuclear weapons testing from the 1960s. So whenever you see the spike in cesium-137, then that's around the year 1965. So that is how you can determine if this is above or below that 1965 time marker. That's how you can date recent sediments, by looking for cesium-137. So this shows all these sand layers in very, very recent sediments. But we're not satisfied with that. I'm never satisfied with just looking at little cores like this. Let's look at longer cores. Let's see what happens when we look at longer cores. This is a study, we're kind of going back in time a bit, But this is a study from 1993 that really put paleotempestology on the map. This study has been cited hundreds of times. I think it's like 850 times the study has been cited. So this was Lewin Fur in 1993. A lot of stuff that you can't see. The main parts are that they use Hurricane Frederick, direct impact, Category 3 as a modern analog, but they only found Hurricane Frederick in the nearshore cores. So they went way out in the middle of the lake, took sediment cores, and found sand layers that are from intense hurricanes that they argue is more powerful than Frederick because Frederick did not leave a sand layer right here. So we're talking about very strong, intense hurricanes that can essentially have storm surge to deposit sand in the middle of this lake. I often argue, kind of tongue-in-cheek, that we know that these are from hurricanes unless, people on vacation in these areas sprinkle sand in these lakes just to mess with me, okay? But I say that kind of loosely because we take transects to determine that the sand layers are thick near the coast and they thin out with distance. So, but this is a very nice place to work, the U.S. Gulf Coast. There's no tsunamis. Winter storms are not strong enough to breach this sand barrier. We have really good sea level records. So we are extremely confident if we see white sand here, there's no other depositional mechanism that could transport into the middle of the lake besides intense storm surge from a hurricane. So we have 11 direct hits in 3,200 years. So they count 11 sand layers, 3,200 years. So they have one direct hit every 300 years from a hurricane. And these are very intense, like I said, more intense than the Category 3 Frederick. So these are 4 and 5s, more than likely. Let's go on to another site. This is Western Lake in the Florida Panhandle. So this is lost on ignition. I'll talk about this in a moment. All these little dips, you see all these spikes in water content. This is a sediment core. All these little dips are hurricanes. So you see all these little lines. This is called the litholog. This is a very generalized depiction of a sediment core. So you have all these lines. Now you have, this is on a date scale. So this is radiocarbon years before present. So what's interesting about this is that we have a 7,000-year record. This may have caught your eye. Maybe it didn't. But you see all the sand layers are wedged right here. They're all right in this time frame right here from about 1,500 or 1,000 to about 3,400 years BP. You have nothing, not one sand layer from 4,000 all the way down to 7,000. So you have right here, this is a hyperactive period. This right here is an inactive period. So this right here is displaying that on multi-centennial to millennial scales, you have hyperactivity. A lot of hurricanes, no hurricanes. So it was the dialogue around the lab, right after this happened and beyond, that if we think that it's active now on the Gulf, we really haven't seen anything yet. We really have not seen anything yet because we are currently in an inactive period on a multi-centennial time scale. Now, this was from 2000, so this is a few decades old, right? So it'd be interesting to go back and see if there are more sand layers here, if they register more sand layers. But the activity was from about 1,000 to 1,500 to about 3,500 years BP. Very frequent hurricanes, very frequent. So 12 sand layers in 3,400 years, a similar one per 280 years as in Gulf Shore's Alabama.
Can I ask you one question?
Yeah.
So those sand band is with level of category 4 or 5 hurricanes. How about those smaller ones? Do you think that it can bring the add to a layer or not?
Well, see here, you can get those records right here, but you have to be careful because some of these areas may be very sensitive that you would get more, you may get more than hurricanes. You may get more minor breaching.
Yeah, because my feeling is the frequency, like 1-300 years, is kind of less than what I expect.
Yeah.
If we count all kinds of hurricanes. So, which makes me think also the thickness of the sand band could be different. Is that a factor, like to be precise, 4 or 5, or just smaller? Because each band is different thickness, you know?
Right. So we look at all those. We look at the thickness, and we look at the frequency as well. So different areas of the lake, you would get different sensitivities. You would get different types of records.
Yeah. So how do you match this sand property to the category of hurricanes? That's my question. Like, for example, 4, 5, do you see a difference of the thickness of the sand band?
Yes. Well, here in the middle, it will be only 4s and 5s. Here in the near shore, the 4s and 5s will be thick. They'll be very thick. Because they will be thick, because that's how the model works. They'd be thick in the near shore, and that they would thin out with distance inland. Yeah, yeah. That's a good question. You may be asking yourself, what caused this? What caused this hyperactivity? So right here, these are all records from the Gulf Coast. Pearl River Marsh, Pascagoula Marsh, Lake Shelby, and Western Lake. This is all on the Gulf Coast. What's interesting with this is that you see all right here, they had the same activity regime, more or less. They were all active around the same time, in the 1,000 to about 3,500 year before present. They were all active. You see a lot of sand layers in all these cores, not a lot on top, not a lot on the bottom. What's really fascinating is that if you compare these records to records on the Atlantic coast, it's flip-flopped. So these are records from Red Wing Lake. This is in Virginia. This is Nobscapon. I think Nobscapon is in Rhode Island. It is antiphase. So when it was active in the Gulf, it was largely inactive during this time period on the Atlantic coast. When it's active on the Atlantic coast, it's inactive on the Gulf Coast. So we have these kind of antiphase drivers, and that led to a very, very important climatological paper in 2000 by Dr. Jim Elsner from Florida State, the Bermuda High hypothesis. That essentially the Bermuda High hypothesis, this high pressure system right here, the Bermuda High, which is always kind of wobbling, when it is positioned more so in the middle of the Atlantic, hurricanes essentially go around it like a slingshot, and they hit the Atlantic coast. When this wobbling Bermuda High makes its way further down into the Florida area or I guess the southern Atlantic Ocean, hurricanes can't go through it, they go around it. And they make landfall in the Gulf Coast. So this is the Bermuda High hypothesis, but this shows how climatological mechanisms, not related to ENSO, not related to the AMO, how they play a part into hurricane frequencies. This was also a very, very well-cited paper. Now, I don't want to get too involved with methods, but I want to show you some of the really interesting methods that we use to find hurricane evidences. So geological techniques, very, very basic tests called loss on ignition. You essentially take sediment and you ignite it at all these different temperatures, 105, 550, and 1,000. And when you ignite them to these, you are losing these components. You are losing the water component, losing the organic component, and so on. So a sand layer, because you can imagine, if you have a sand layer that's very, very thin, you can't see it. All right, like I can't dig and see all these sand layers. It might be microscopic. So you use these tests because if there is a sand layer in these sediments, there will be a drop in water. Because it's sand, it's a clastic sediment, it's low in organic, so it'll also be a drop in organics. Lake sediment, marsh sediment is very high organic, at least relatively so. So these sand layers will be a drop in organics. Grain size analysis, this is also very interesting. There's analysis of grain size because hurricane deposits typically fine upwards. So there's coarse sediments on the bottom. This is due to the physics of a hurricane wave. Generally coarse sediments on the bottom and they fine upward. So if we do grain size analysis, these would be coarser sand and then this will be more fine sand. Rip-up class, which also shows kind of a reworking of sand, those are rare in hurricane sediments. So I could talk on and on about all different types of proxies and methods to find evidences of hurricanes. And I can't talk about all of these, but fossil pollen, diatoms, foraminifera. Diatoms and foraminifera are algae, okay? There are marine diatoms. So if you find marine diatoms in your sand layer, it can show a marine source. Because if you go to a conference, if you go and talk about the results to scientists, they will say, yeah, this is cool, right? Yeah, you got sand layers, but how do you know? How do you know that precisely, how do you know that this is from a storm surge event? Okay, so they want additional pieces of evidence. One additional piece of evidence could be from phytoliths. Phytoliths are essentially plant particles. So what's really fascinating about this is that in this study right here, Liu and Liu 2005, you take surface samples, and these are not a depth. This is not a sediment core. These are all surface samples of different environments. So we have fresh marsh, brackish marsh, salt marsh, all these different environments around your coring location. So boom, right here, we have sand dune. So essentially, if we have sand, and if the phytolith signature in your sediment core matches the sand dune, that it's like a fingerprint that essentially matches the sand in your core to the sand dune sand, and it shows a process. So you put all these surface samples onto this ordination space. I don't really want to go into this in too much detail. But when you have these sediment cores, you have these sand layers right here, very nice. And from this phytolith analysis, you compare the sediment core phytolith analysis to the surface sample phytolith analysis, and you get a match. You get what's called the predicted group. It essentially tells you which environment these sand layers match with. So it essentially acts as a fingerprint. These sand layers came from the sand dune, which suggests the process from storm surge.
Can I ask a question?
Yeah.
So you said the fingerprint of phytoliths, but what is the actual fingerprint? Is like DNA? You sequence it?
No.
No, it's
No, so that's a good question. So when we take sediment and we chemically process it, so when you chemically pollen, for instance, and even diatoms and forams, and even phytoliths, you chemically process the sediment, and it removes everything but these microfossils. So you just take these microfossils,
to visualize it.
yeah,
See it.
and count it.
Oh,
It's It's just counting. So it's just someone in a lab has like a printout, and they just count all of these types, and that's it. Same with pollen. You just count it out. So in addition to this, we have chemical proxies, okay? We have X-ray fluorescence. So this is another tool that can help us determine storm surge. This is very, very common now in environmental science, geology, oceanography, and so on. This is very nice because you scan a sediment core and you get concentrations of elements in more or less real time, 60 to 90 seconds. Now, what's very interesting about this is that you are looking for spikes in a lot of concentrations that are high in marine constituents. So marine algae, seashells, and so on and so forth. So those are calcium, strontium, chlorine, iodine, sulfur. There are more. So what makes this interesting is that these are the so-called marine indicators, okay? You may, in a sediment core, have spikes in what are called terrestrial indicators that indicate a terrestrial flood, a fluvial flood, a river flood. So those would be the titaniums and the irons and so on and so forth. So you can tease apart what type of disturbance you have in your sediment core from the spikes in the marine versus the spikes in the terrestrial elements. So X-ray fluorescence is really, really common and popular to determine the sediment provenance, where the sediments come from. So basically, I still have some time. I want to show some recent findings in paleotempestology just to kind of show where the science is going. That I want to kind of end this with my current research project in the Great Lakes area. So here, this is where things have gotten really advanced. This was in 2012. These are all types of paleotempestological findings, and you have active periods and inactive periods. And these are all types of regions, and this field has exploded from the Gulf to the Atlantic, and now it has spread to the Caribbean, to Mexico, to Southeast Asia, and so on and so forth. So now we can look at these records, Puerto Rico, the Southwest Pacific, Belize, Japan, Australia, and we can attempt to correlate activity and inactivity regimes globally. We can better understand these global connections between different ocean basins. So scientists have understood some of these correlations and connections, but scientists are trying to better understand when it's active in basin X, will it be active in basin Y or inactive, and why this is. And this is in comparison to an El Nino record. Now you may be asking yourself, okay, and this is kind of the next challenge in paleotempestology. We work a lot in Mexico. This is common in the Caribbean. This is more common on the west coast of Mexico. Does Mexico have tsunamis? I already ruined it for you, yes. Okay, I already gave it away. So Mexico has tsunamis. Mexico also has hurricanes. And this is really interesting. This is where this multi-pieces of evidence, multi-proxy investigations really come into play. This is not the Gulf Coast. This is not the 1990s in the Gulf Coast, where you just find one piece of evidence, sand, and say this is a hurricane. Mexico is way more complicated. There's hurricanes, there's tsunamis, there's a lot of fluvial floods because it's very dry, but when it rains very intensely. So there are all types of factors, okay? I really like this paper from 2012. This is in the Ixtapa estuary. So they found these very nice sand layers, one right here, and then one right here, and they dug a trench, and they showed these sand layers that go all the way around. And the whole premise of this was to use multiple lines of evidence to determine if these were hurricane deposits or tsunami deposits. So this is very common analysis in Mexico or in Japan or in parts of the Caribbean. We have to tease these apart. These scientists are from Huron, which is in Mexico City. They did all these multiple lines of evidence. So this is grain size, this is chemical elements, this is a titanium-calcium ratio, which shows the forces of the marine versus the forces of the terrestrial sediments. Loss on ignition, but right here, diatoms. Right here, they have diatoms. And if you see right here, maybe you could see you have freshwater brackish marine diatoms for all these layers. But in these sand layers, they were largely broken, or at least half broken. And because of that piece of evidence, because all the rest of the signals can match either a hurricane or a tsunami. They deposit sand, okay, they deposit marine sediments, seashells, and so on. They argued that these were historical tsunamis because the turbulent waves of a tsunami are more likely to cause breakage to these diatoms. So they argued that these are not from hurricanes, that these are from tsunamis. And it was controversial, and it kind of led to a lot of discussion, but this is what was published in 2012. So this is how you use multiple proxies to best tease out what type of extreme event it was. Because if it wasn't for the diatoms, then it possibly may have been led or believed that these were deposited from hurricanes. More recent findings, South Korea, 5 shell gravel layers, and they correspond to the little ice age in the medieval warm period. So again, we are really expanding and working in areas throughout the globe. This is not my group. This is Yang et al. 2017. So South Korea, there's record. Really fascinating record from Cuba. And this is Matt Peros, 2015. He is at, I believe, the University of Winnipeg in Canada. What's really fascinating about this is that you have these spikes. Yeah, you have these spikes right here, and these spikes are indicative of sand layers, coarser grains. So coarser grains being pushed into these coastal environments. What's really fascinating is that he correlated these spikes with this right here, charcoal. So what they found was that these spikes that they attribute to sand layers are also correlating to spikes in charcoal. The spikes in charcoal are from fires. So there is a hurricane fire link, because as you can imagine, nowadays, if there is a hurricane, it demolishes a forest and it becomes dry. That's litter and that's fuel for fire. Lightning comes, and then that's how forest fires happen. So nowadays, when there's a hurricane, you have crews that come and clean up all this debris. Back 500, 1,000 years ago, they didn't have that. Okay, there weren't these groups that cleaned up these debris. So you have these spikes in charcoal that are synonymous with these fires. So it shows this kind of hurricane fire link going back many hundreds of thousands of years. So these were findings from Cuba. These were recent studies. This was from our group, Yao et al. 2019. These were studying the San Bernardino National Wildlife Refuge in Texas. Now this shows some of the complexities of paleotempestology. We talked about how Hurricane Harvey, it rained, it stalled, it flooded. So Hurricane Harvey brought storm surge. Hurricane Harvey also brought a lot of river flooding. So we took all of these sediment cores, and you see the San Bernard River. If you see some of this brown, it was a whole muddy mess, okay? It was a whole muddy mess, and this is some of the most severe flooding the San Bernard River has experienced in quite a long time. So we were trying to determine if we could find a signal from Hurricane Harvey to act as a modern analog to show the flooding from the storm surge and the flooding from the fluvial component. So being a scientist, you can look for some cues and some clues to the impacts of these hurricanes. So if you just went out to this area, you got an idea of how high the water levels were, because all the shrubs were all muddy and nasty. Okay? This is mud, but it's dry mud. This is Texas, it's very hot. So you have the water level this high, and it deposited all this mud, and you have all this mud on all these grasses. This was measured at about 85 centimeters high. So we knew that water levels were at least that high in this area. So we wanted to get the sedimentological imprint and fingerprint of this hurricane. Now, this is the challenge in paleotempestology. It doesn't always work out the way you want to, but that's science. So I always tell my students that. Sometimes your hypothesis does not come to fruition, and they get really discouraged, and they get discouraged. I tell them all the time that that's science. Very, very distinct flood deposit here, likely from Harvey in all these cores. Sand was minimal. The sandy beach in this area was very, very thin. We did not get much of a marine signal from Hurricane Harvey. That was a very tremendous, very fierce and strong event. This is very, very small to see, but this layer way up here in all these cores, this could not be distinguished from the sediments below because we are in a floodplain of a river. So the Hurricane Harvey imprint from the river flood was really no different sedimentologically from normal river floods. We could not really tell them apart in terms of grain size or XRF. But we do have this little spike in what we call the ratio of chlorine to bromine. The chlorine to bromine ratio is a very, very reliable and published proxy to determine marine water inundation, seawater spikes. So we have this little spike right here at the base of these layers, but beyond that, we cannot find much of a chemical imprint from Hurricane Harvey. So this was published as kind of a food for thought for better ways to find this event, because if we can best characterize this event, then we can find older events in the sedimentological record. So this is a challenge in paleotempestology. So the future of paleotempestology is there are countless tasks and future goals. One of them is to essentially fill in a lot of these gaps. There are a lot of gaps where we need records from Canada to Maine, all the way to areas in Central America, Belize, Honduras, Nicaragua, many, many areas of the Caribbean Isles. Many areas have few records or no records. Large swaths of Florida are still lacking long-term records. So those are useful for climatological records, to determine forcing mechanisms, and also for risk assessment. Very, very important. I was in Puerto Rico this past summer because I am funded a National Science Foundation project to determine or find the analog. We talked about modern analogs, to find the analog from Hurricane Maria. So if we find the geological signal from Hurricane Maria, not only in coastal areas, but also in interior areas, we can use that signal to better understand similar hurricanes going further down in the sediment cores, to better and more accurately reconstruct hurricane and flood records going back hundreds or thousands of years. So this is currently in progress, funded by the National Science Foundation. Now, probably about 10 minutes left. I'm a professor. You know that I'm going to give you a quiz, okay? So some of you may already know this in the room. Does the Great Lakes experience hurricanes? No. I will take that as a yes, and you pass. Yes, they do. Now, that was kind of a trick question, but there are systems that impact this is my current research in the Great Lakes. There are systems that mimic hurricanes that impact the Great Lakes. Now, all these lines, they kind of come up from the southwest and kind of travel northeast. These are extratropical cyclones. So extratropical cyclones, they hit the Gulf Coast, they lose a little bit of steam, but they become kind of cold core cyclones, and they make impact along the Great Lakes, cause really intense flooding. Very, very common. For those that didn't answer that, you have one more chance. You have one more chance. Does the Great Lakes region experience tsunamis? Tsunamis, I didn't talk about this. A tsunami, if you do not know, is a tectonic event. It is driven by displacement of ocean bottom, oceanic crust due to an earthquake, okay? And that causes a wave. Different type of a wave, different type of a wavelength than a hurricane or a storm. So with that hint, do the Great Lakes experience tsunamis? You know you want to say it. No. A no and a yes. The answer is yes. But again, I'm tricking you. They're termed mediotsunamis. Now, study in 2016 talked about all of the mediotsunamis that impact the Great Lakes. And look at all of these damages we're talking about. Death and injury and events per year all along the Great Lakes. So there is immense flooding from these mediotsunamis. Mediotsunamis are caused by all types of weather events. They're caused by drops in pressure. They're caused by winds. These are similar to quote-unquote cyclone flooding, but the wavelengths are different. It's a different type of a wave. So that's what differentiates a mediotsunami from a cyclone tsunami. Similar, but not similar. So the answer is yes and yes, or yes asterisk and yes asterisk. So yes. So this is a really important problem. No one has ever looked at this in the Great Lakes, okay? So I brought up these topics in lectures in 2018, and the response was a lot of scientists did not even know that these were problems in the Great Lakes, okay? To attempt this paleotempestological reconstruction along the margins of the Great Lakes. The Great Lakes are beautiful. Great Lakes are beautiful, okay? The Great Lakes have a ton of environmental issues that we may or may not be aware of. If you have seen or read about Lake Michigan, for instance, Lake Michigan's gorgeous. Lake Michigan, Lake Erie, there are record high water levels. The record high water levels cause what? They cause erosion. You see beach houses and vacation houses on Lake Michigan, they're falling into Lake Michigan. Not talked about as much as it probably should be. This is a problem. This has received much attention lately from the U.S. Army Corps of Engineers and the DEQ, which is the Department of Environmental quality. So storms cause flooding and erosion along the margins of the Great Lakes. 2.9 billion with a B, in damages. This is an older study, 1995. Now, here we have, and another thing, I forgot to mention this, Hurricane Huron. Hurricane Huron was a storm that mimicked a hurricane that formed over Lake Huron. Formed with a core and an eye, formed over Lake Huron. So we have all different types of storms. This is also a region that is very unique climatologically because you have polar air from the north, you have tropical, subtropical air from the south. Okay, so this could be a very turbulent area. Extratropical cyclones like the ones I showed in the last slide. Seiche. There is things called a seiche. So this is another type of a flood. This is caused by wind. The Great Lakes, they're enclosed. They act like a bathtub, okay? Literally, you can have storm surge that impacts New York. And the high water in New York, when it stops, the bathtub floods the other way, and you can get flooding in Ohio from storm surge in New York, okay? Those types of events, wind events, drops in pressure, those are termed seiche. Different than a medial tsunami, different from a cyclone due to the wavelength. Lake level data is sparse. Residential properties and commercial businesses at risk. In addition to that, wetlands are very, very important, okay? What's really interesting about the state of Ohio, in, I think, 1900 or 1910, yeah, the stats right here. Ohio has lost 98% of its wetlands since 1900. It was called the Great Black Swamp of Ohio, drained. Drained for infrastructure, drained for agriculture. Wetlands are very important areas. They stop waves. They essentially hold the energy from waves. They buffer this energy. Important for water quality and property and so on and so forth. The wetlands are the perfect repository to find evidences of floods. Find evidences of these floods. It has not really been done before. This was a study from 2006. They took a bunch of sediment cores, but this is on the Canada side of Lake Erie. But their cores were a little bit too far away from the lake. I wanted to go a little bit closer to the lake to see if I could get some of these sand deposits. So that's what I did. Also, if there were floods, I wanted to see how the wetland, how it held these floods, how the vegetation damage was. Did it disturb the wetland? You can find all this with a paleoenvironmental reconstruction. So, I want to wrap this up really quick. I think my time is nearly done. 3 field seasons from 2 sites right here, kind of close to the Michigan-Ohio line. All of these sediment cores from Cedar Point National Wildlife Refuge. That's not too close to Cedar Point. It's not like I was taking a break and riding the I don't know what's called, the biggest roller coaster is at Cedar Point anymore. I'm getting too old. McGee Marsh. So sediment cores from both of these lakes to try to find flood damage, flood deposits. Just walking around these areas around the Lake Erie margins was very promising. These shell lobes signal and suggest overwash. The fact that they're fresh, quote unquote fresh, by fresh, there's not a lot of vegetation on them, okay? They're not buried. So with this, it signals and signifies that these are recent. A lot of sandy beach, sand gets essentially pushed on, it's called littoral drift. It gets just deposited along the margins of the lake naturally. And then this is me. It's all every professor needs a picture of him holding the sediment core. Okay, I just got back from ankle surgery. I didn't do any sediment coring. Okay, my student did. This is just him giving me it for the photo op. So very, very preliminary results is right there, right here on the core with the big yellow pin. Right there is a sand layer. What's interesting about this, you see the dip in the water in the organics. This is dated to 720 years BP. Okay? What's fascinating about this is that this event must have been so significant and severe, nothing else has happened of similar magnitude before, and nothing else has happened of similar magnitude after. So whatever happened here is significant to deposit this thick 5-6 centimeter sand layer into this coastal margin. What's also fascinating about this is I lined up all kinds of sediment cores. This is distance from the lake. So this is close to the lake. This is far from the lake. 115 meters from the lake, 206 meters from the lake. So this is a transect. What's fascinating about this is that the sand layer was present. Ooh, for this core we have 2 sand layers. That's really cool. Present, whoa, absent. So this suggests, because someone's going to ask, some reviewer, scientist is going to ask, how do you know this came from the lake? That this didn't come from a river flood or from human disturbance? This is circumstantial evidence, but we're working on more evidence, but this is circumstantial at the moment. But this is good proof. Present, absent. The problem is my dates are all over the place. 1947 years ago, 720 years ago, 1800 years ago. So I cannot get a good date of this event. So there could be contamination. It could be lab contamination. I'm trying to figure out why my dates of this event are all over the place. That's something I need to work out and figure out. So I have plans to do similar research all over the margin of the Great Lakes. I have found many sites. I need good students and colleagues to help me because I cannot do this all by myself. This is overwhelming just to look at. So these have been found. There's criteria. I'm not just picking these just to pick them randomly. These are low-lying areas, protected areas that human disturbance is limited. You need a permit to get into a lot of these areas. These are managed by Fish and Wildlife Service or DNR, Department of Natural Resources, all over from Lake Superior, Lake Michigan, Wisconsin, Michigan, Ohio, and so on and so forth. This is the last slide. This is the Coastal Hazard and Environmental Reconstruction Lab if anyone is interested. My website is here. I have business cards with me. I would love to stay and talk with anybody about anything that pertains to this talk or research. I would love to talk about anything. So you see the objective of our lab and all types of the really, really cool and innovative and interesting research that we do in paleoenvironmental reconstruction. Yeah, thank you very much for your attendance. Thank you very much. And I will answer any questions up here or in private, however you want to do it. So that's it.